Hello, today we are going to present our progress on developing an autonomous drone for nuclear inspection. In 2011, the Tohoku earthquake and tsunami damaged the cooling mechanism in the Fukushima nuclear plant and caused 3 nuclear meltdowns, 3 hydrogen explosions, and the release of radioactive contamination which necessitated the evacuation of 100,000 residents. This disaster highlighted the need for low-risk and efficient inspection technologies, both pre- and post-disaster. Our product aims to revolutionize a variety of safety-critical inspection tasks with an AI-powered drone named Capstone. Our first target application is nuclear inspection, where our product will improve the safety of nuclear facilities with more routine and thorough inspection and enable rapid response to emergencies. This presentation is an invitation to join us on this mission with your investment. Our team is made of leading robotics industry experts who are ready and excited for the challenge of building an autonomous drone. Ben is the lead software and simulation engineer. He has experience from his time at the autonomous vehicle company Waabi and various prominent research labs. Jerry is the lead hardware engineer. He has experience from his time at Quantum Robotic Systems. Connor is the team lead for management and design as well as a contributing member in autonomy planning. He has a background in robotics and autonomy from his time at Applanix Trimble and Celestica. Cameron, our lead computer vision engineer, possesses a diverse background with an Intel FPGA internship and a keen interest in computational biology. His broad experience is a valuable asset to our autonomous drone project. The first tenet of our team's design philosophy is simulation first. Simulation allows for rapid development, with quick iteration on hardware and software designs, and robust testing and pre-flight verification, making the development process more safe and efficient. Our team has built a simulation of our testing environment, as shown in this video. We continue iterating on this simulation to make it more complete and accurate. Here you can see raw topics published by our controller during the simulation. Our drone's position is shown with the coordinate axes, the global plan is shown with the green lines, and the waypoint tolerance is shown with the red spheres. Our simulation includes simulated Intel RealSense T265 with odometry and fisheye camera topics. This will be critical in the development of obstacle avoidance and other future computer vision systems. We also leverage the ground truth pose information to provide simulated Vicon data. In cases where simulation is not possible, we plan to use log replay. This is where we record data from the real drone and assess our algorithm on this data. This can be used to assess and minimize the sim-to-real gap, such as that in the T265 fisheye camera rectification algorithms which rely on specific camera calibration values. The second tenet of our design philosophy is future-proofing. We want the solutions we develop now to incur minimal technical debt moving forwards. For example, from the beginning we set up our development platform to use the latest and greatest hardware, operating system, and software package versions. This provides the best and most future-proof development platform for our code to be written on. Our navigation stack is also designed with future-proofing in mind. For our second milestone of hovering, we already had a global and local planning framework, which is easily extensible to future features like obstacle avoidance. The third tenet of our design philosophy is simplicity first. We choose to use off-the-shelf hardware and open-source implementations wherever possible, including for simulation, robotics operating systems, SLAM, and flight control. We avoid over-engineering and exploit the structure of our tasks to devise the simplest possible solutions. As such, our code is contained to a few hundred lines of Python. Our system consists of 3 main modules: the ground station from where commands and other information are sent, the onboard navigation system, and the drone hardware, complete with sensors and flight controller. The ground station has various services which constitute high-level semantic commands for the drone, including launch, land, abort, and test. Further detailed information can be sent to the onboard system through topics, such as desired waypoints in the global frame, and Vicon global poses. This framework is easily extensible to send additional information to implement future features. The onboard system consists of 2 components: the global planner and the local planner. The global planner is responsible for receiving and processing information from the ground station. The global planner computes the transformation between the local map frame and the Vicon dots frame using the position estimate from the flight control unit. Further, it computes the necessary transformations to turn the waypoints in the global frame to those in the local map frame, and maintains a thread-safe queue of waypoints to visit. The waypoint queue is augmented based on the information from the ground station, such as clearing it when aborting or adding waypoints when testing. The local planner receives the current goal point in the map frame and the estimated pose of the Vicon dots frame in the map frame from the global planner. The local planner is then responsible for computing the desired twist of the flight control unit in the flight control unit's frame, such that the drone navigates towards the current waypoint. The local planner has various modes which are selected by the global planner, including non-holonomic and differential drive, which enact different flight behaviors depending on the task. For example, differential drive treats the drone as a differential drive robot that must always fly forwards, in the direction of the camera, which is useful for obstacle avoidance. These modes can easily be extended to implement future features. With this system setup, the hovering and waypoint navigation milestones were simple. Here is a video of Captor performing waypoint navigation. Notice the smooth flight patterns that closely match the simulation. The next development milestone is waypoint navigation with online obstacle avoidance. The drone must fly to a sequence of waypoints while avoiding unknown obstacles. It must travel on the right of green-banded obstacles and on the left of red-banded obstacles. The first challenge we foresee is obstacle detection and color recognition. We need to both localize the objects relative to the map frame and recognize if they are red or green. Using our forward-facing Intel T265 causes two difficulties in this regard. First, the fisheye images are grayscale, so color detection is non-trivial. To solve this problem, we will use images of the known colors to calibrate our recognition algorithm. Second, the T265 camera does not provide depth information, which is necessary to localize the obstacles. There are two solutions to this problem. The first is to undistort and rectify the fisheye images to be used in stereo depth estimation. The second is to use the known dimensions and orientation of the obstacles to estimate their position. The second challenge is implementing a local planner that can avoid these obstacles. Our first proposed solution is to use a pre-programmed maneuver that depends on the obstacle color, given the known obstacle dimensions and estimated position. The second proposed solution is to use a dynamic window approach to generate candidate trajectories, score them to avoid obstacles on the correct side, and choose the highest score trajectory. There are wide-ranging applications of the drone technology we plan to develop. Applied to defense, Captor will provide critical support in intelligence, surveillance, and reconnaissance missions, empowering decision-makers with real-time data while minimizing the risk to personnel. For law enforcement, Captor will improve decision-making with information from the sky. Captor will help firefighters and rescue teams by quickly scanning vast areas to identify potential survivors, increasing the chances of successful rescues. In hazmat operations or at disaster sites, Captor will safely and autonomously provide essential information for response teams. Applied to bridge inspection, Captor will provide faster, more complete, and accurate data with reduced risk. By scanning and creating 3D models of cell towers, Captor will inspect critical network components, ensuring the reliability and safety of communication networks. Captor will streamline construction site processes, including planning, progress monitoring, site surveys, and as-built assessments. By spotting issues faster and monitoring hard-to-reach places with less risk, Captor will transform the way power plants are inspected and maintained. With fast response to outages and issues, Captor will provide low-risk aerial assessments, ensuring the stability of distribution networks. Autonomously capturing breathtaking cinematic shots, Captor will elevate the creative potential of filmmakers and outdoor enthusiasts. We appreciate your attention and hope you share our enthusiasm for this opportunity. Thank you for watching this presentation and considering joining us as a partner in this venture.